Today, we're going to talk about something wild. We're going to dive into just one single PhD thesis from 1957. In this thing, written by a young physicist named Hugh Everett III, it didn't just tweak a theory. Oh no, it proposed a whole new way of looking at, well, everything.
So you have to understand, back in the 1950s, quantum mechanics had this deep, really strange puzzle at its heart. I mean, the theory worked like a charm, but it had this weird split personality. It had two main rules, right? But one of them, the really bizarre one, it only seemed to happen when we were actually looking. So the big question was, why?
Right, so before we get to Everett's incredibly elegant solution, we've got to get our heads around the problem he was staring down. And it was a big one. He was looking at a theory that, for all intents and purposes, followed two totally different sets of laws. And the decider? It all seemed to depend on whether or not someone was watching. Okay, so here it is, the split personality of quantum theory laid bare. On one hand, you've got what they called process 2. This is what happens when you leave a system alone. It just evolves. Smoothly, predictably, continuously. It's all described by a nice wave equation. Totally deterministic. But the second you look, the moment you take a measurement, bam, everything changes. A totally different rule, process 1, just takes over. And this one is a sudden, random jump where the system collapses into just one of its possibilities. So how can both of these things be true? How can the universe play by two different rule books? And look, this wasn't just some weird philosophical thing to debate over coffee. No, this led to some really serious practical questions that the standard theory just had no answer for. I mean, think about it. What happens when the observer is part of the system you're trying to describe? Or what about a measurement that isn't perfect, just kind of approximate? And here's the real kicker. How in the world do you apply these rules to the entire universe? I mean, you can't step outside the universe to measure it, right? So does that random jump, process 1, even apply to reality as a whole? It was a real crisis. And this is the crisis that set the stage for Everett's proposal. And it was beautifully simple. And absolutely radical. Everett's idea was kind of like theoretical surgery. He looked at these two competing rules and basically said, you know what? What if we just get rid of the weird one? I mean, what if process 1, that sudden random collapse, what if it doesn't actually exist? What if it's all just an illusion? And this right here is the heart of his idea. Taken straight from the paper, he proposed that pure wave mechanics, process 2, is the complete theory. It describes everything, everywhere, all the time, no exceptions, no special rules for when you're looking, no collapse, just one single, elegant, universal law. Okay, wait a second. If the wave function never collapses, then what in the world is a measurement? Why does it look like it collapses every time we check? And that question brings us right to the conceptual heart of his paper, something he called the relative state. So here's the crucial idea. Everett says it's completely meaningless to ask, what is the absolute state of this particle? You just can't. A thing doesn't have its own independent state just floating in a void. It only has a state relative to whatever it's interacted with. It's all about the relationships between things. Okay, let's walk through what this actually means when you do a measurement. So before you look, you, the observer, and the little quantum system, you're separate things. You're independent. Then you interact. You perform the measurement. Now, it's what happens after that's the key. You're not independent anymore. You and the system have merged into one single larger system, and your states are now fundamentally linked. They're correlated. Or as physicists say, they're entangled. The state of you, the observer, is now defined only in relation to the system state. And this is where things get really, really weird. I mean, truly mind-bending. If you, the observer, become part of the system, and there's no collapse into just one outcome, what on earth happens to you? Well, instead of one outcome being magically picked out of a hat, the whole thing, the observer and the system together, just evolves into a giant superposition of all the possible outcomes. The wave equation just keeps on doing its smooth, deterministic thing. Let's try to picture what that actually means. Okay, let's say you're measuring the spin of a particle. It can be up or it can be down. Now, in one part of this new, bigger superposition, we can call it a branch, there's a version of you. And this you definitely saw the spin as up. Your memory recorded up. And in that branch, relative to you, the particle is spin up. But, and this is the whole point, that's not the end of the story. At the exact same time, in another part of that superposition, another branch, there's another version of you, an equally real you. And that you definitively saw the spin as down. That you's memory says down, and relative to that you, the particle is spin down. Both things happened. Both outcomes are real. Everett himself described this as a branching tree. Every single time a quantum measurement happens, your state, well, it splits. Each branch is a different, concrete outcome. And here's the kicker. All the branches are equally real. They all exist at the same time in this massive superposition. And this part is crucial. From inside your branch, you have absolutely no idea the other branches even exist. You can't see them, you can't feel them. The split is perfectly clean. Okay, this immediately brings up the question that I'm sure you're screaming right now. If this is true, why does my world feel so normal, so solid? Why do I only remember seeing one outcome? Why does it feel like there's only one of me? And Everett's answer is just brilliant. He says that from the perspective of an observer inside any one of those branches, the world looks completely 100% normal. It looks exactly like the old rules were true. It looks like a random collapse really did happen. The illusion of chance, from your point of view, is perfect. And then he backed it up with the math. He showed that if you try to assign a kind of weight or measure to each branch, how significant it is, there's only one logical way to do it, and it turns out to be the square of that branch's amplitude in the wave function. And when you do that, it perfectly reproduces the famous Born rule for probability, the very rule that physicists had been using for decades without really knowing why it worked. Everett just derived it from first principles. So this is the big takeaway. In Everett's universe, probability, it isn't fundamental. Chance is not a basic law of nature. It's something that emerges from your perspective. It's a consequence of the fact that there are countless versions of you, and the weight of the branch that your version is on determines the odds you seem to experience over time. And what's so amazing is that this totally radical idea, it puts our familiar world back together again perfectly. You measure something twice, you get the same answer, because you're still in the same branch where that was the answer. You and your friend measure the same thing, you'll agree on the result, because you're now correlated, you're in the same branch of reality. It even explains things like the uncertainty principle. It all just clicks into place. So in the end, Everett's thesis leaves us with this startling but completely self-consistent picture. A vast branching reality where every single quantum possibility actually happens. And that leaves us with one last pretty wild thought. Just in the time you've been listening to this, countless tiny quantum events have happened. In your brain, in your screen, all around you, creating a near infinite number of new branches. So the version of you hearing my voice right now isn't just one of them, which makes you wonder, what are all those other versions of you doing right now?